Thank you all for coming to this talk. I would like to say that I really love programming conferences because there's so much new information I can learn, and learning is like one of the greatest feelings. And also when you can join the dots, and speakers often provide this insight that can join information that was previously distant in my mind. It just helps to form this knowledge. But there's a greater feeling than learning new stuff, and it is unlearning the stuff that you got wrong. And for me, I remember the first time I felt that feeling was when I was taking the course on Coursera, which was called Model Thinking. And one of the models they were presenting was normal distribution. And usually people know what is normal distribution. So if you have some random data and it follows this distribution, you can calculate the average and standard deviation. And within 3 standard deviations from the mean, you get 99% of data points. But the example on the course was about real world, and it was about overbooking flights. And when I first heard that, I was like, I must have got that wrong. How could you overbook a flight? If I would create a database system for flights, the first constraint I would put is there can't be more bookings than seats. However, it makes sense if you think about it, because let's say we have a plane with 200 seats, and usually about 20 people don't show up, and the standard deviation is 6. So if you overbook 20 minus 3 standard deviations seats, which is in this case 2, there's 99% chance you'll be perfectly fine. And in this one chance, in this one flight of 100, you will just refund the ticket for this poor guy, and at the end, maybe not even that poor, because he will fly for free and may even enjoy that. So at the end, we sometimes think that our system needs a constraint, but that's not actually true. And there are many such things, both in financial systems and in Elixir. So I want to divide my talk into like 2 parts. The first will be about properties of financial systems, and the second one will be about properties of Elixir and why does it match this domain. So the first thing and the first question I would like to answer is, are financial systems ACID or base? So let's define both terms. So ACID is something that we probably all know. It's about databases and basically SQL databases. So ACID stands for atomicity, consistency, isolation, and durability. And there are 2 things that I would like to focus on in this definition. So first thing is consistency, and this is the first definition of consistency today, that any transaction will bring the database from one valid state to another. So it's only about what is inside the database. So the thing that is inside must be consistent and must follow some rules. The second thing is isolation, and it says that concurrent execution of transactions results in a system state that would be obtained if transactions were executed sequentially. And this sequentially is a really strong word here. The other definition is that the transaction will behave as if it is the only operation being performed upon the database. So let's say we want to distribute a database that follows those conditions. So we have 2 nodes, and they need to have the same data. So we just replicate all the data. However, there are 2 processes that write to this database. One of them hits node A, second one hits node B. And at this point in time, because the data needs to be seen as sequential by both processes, they need to communicate. But they communicate over unreliable network. So if the network is down, they just can't perform the write. They're unavailable. And this is what CAP theorem states. It says that there are 3 properties of distributed systems: consistency, availability, and partition tolerance. And you can only choose 2 of them. And given that partitions will just happen we basically trade between consistency and availability. So this is a second consistency definition today, and it is consistency in cap theorem. And it says that every read receives the most recent write or an error. So it's more connected to the isolation definition from the ACID than to the consistency definition. However, yeah, it's really simple. And now there's a third consistency definition, which is consistency in consistency models. So I said that we can trade consistency for availability. And the third definition says that consistency is set of rules that must be followed by transactions. So this is really vague and works better on an example. In consistency models, there is, for example, strong consistency, which corresponds to this consistency from cap theorem. It says that you either get the most recent write or an error. But there's also weak consistency, and weak consistency is also a little vague because it says that you will get the most recent write if some conditions are met. And then we can specify those conditions. For example, one of those conditions could be if enough time passes, we will get the most recent write. And it is called eventual consistency. So it's a subset of weak consistency. And in the eventual consistency, we can also create another subset, which is casual consistency. And it means that if the transactions are related to each other somehow, they will be seen in order. And a subset of that, again, is, for example, read your writes consistency. So the casual relationship that we defined is that if one entity writes those transactions, or one process writes those transactions, they are connected and they will be seen in order. So we can see that it's sometimes problematic if we talk about consistency because there are three different things that we may want to talk about. How this works in practice. So like in very simplified model, we again have a database, but this time it trades the consistency for availability. And if both processes write something to the database, they immediately succeed. The database is available. And then later, they may synchronize what is in them. And sometimes we lose some information. So for example, here we lost the notion of which transaction was one after the other. So they're both there. However, we don't know if the order is the same on both systems. And that is totally fine for many cases. And this kind of systems are called basically available, soft state, eventually consistent. So the question is, are financial systems ACID or base? And I thought for a real long time that they have to be ACID. And I remember that one of the first examples of mutexes on concurrent programming was about balances. So let's say that Alice wants to send money to Bob, and she sends him, for example, 10 zlotys or 10 euros. So we first calculate, we check if Alice has enough money on her balance, then we subtract this from her balance, add this to Bob's balance, and this is now stored in some variables, and then we actually update the Alice's balance and Bob's balance. However, in concurrent programming, the process may be preempted at any given point in time. So let's say that this process stopped working where the line currently is, and then someone sends Bob $1 million. And he's very happy to get that money. However, after this process sending $1 million ends, then the first process kicks back in and sets the Bob's balance back to this 10 zlotys or 10 euros. And Bob's is very sad about it, obviously. So Of course, this is a great example of mutex says because you would have a mutex on entire transaction, but this is really bad example of how financial systems work. So no one in their right mind would do that. Basically, what you do is you always start with a balance of 0, and then you have a set of transactions that can't be mutated at all. So, for example, an example of transaction is send 10 zlotys from Alice to Bob, and this transaction will be on both of their accounts. And then if we want to calculate how much money they actually have, we simply add all those things. And in case of Alice, because it's in the from part, it will be minus 10 zlotys, and in case of Bob, it will be plus 10. So, question for you. Are financial systems ACID or base? And the answer, like in everything in IT, is it depends. So, for example, if we have a PayPass, like in Poland, you can just swipe your card if you buy something under 50 zlotys. So this is a case of base transactions. So the amount on your bank account can be subtracted 1 or even 2 days later. And it will be definitely out of order. But if you're buying things for more than 50 zlotys, you have to enter your PIN code. And in that case, the transaction is almost immediately on your bank account if you want to check it online. So this kind of transaction actually is ACID. And even more, if you want to send a big amount of money, is there a question? Yes? Yes, but this is also another case. So we can't update transactions. This transaction is not updated. The refund is another transaction that is placed on top of that one. So this is actually ACID. So, and the other case I wanted to talk about is when you send a big amount of money, like for example, 20,000 zlotys, and it isn't a usual amount that you send, you get a call from the bank. So this is like the most ACID as it can get if you involve a human being in the commit to the database. Okay, so if we know that financial systems can be sometimes ACID and sometimes base, let's now talk about Elixir. So I had a talk last year about Elixir and Elm, and I also started with cap theorem because I wanted to show that some properties of those languages are nicely connected to this theorem. And when I stopped talking, someone from the audience asked me, okay, but what do you do at Club Collect with Elixir? So I said we had this financial system and we take money from club members' account and pay it to sports clubs, so they don't have to do the accounting and they have their money on a weekly basis, and we can even allow paying by installments. And the answer was really surprised. Oh, so you can do financial systems in Elixir. And then I realized that there are two things that I didn't say. And first thing is that in our case, we can trade the availability for consistency because we're using direct debits and they're processed in 1 or 2 days. So basically, if they are out of order, we don't care. And second thing is that even though Elixir is a language that makes trading consistency for availability easy, you can totally ignore that. You can ignore this fancy stuff, and there are many other benefits. So another question for you. If you could choose, because we actually can choose, our system doesn't have to be perfectly available and it doesn't have to be strongly consistent. What do you think? What database solutions did we choose? Almost. Like we just used Postgres because it's the simplest solution. So in cases where you can decide where you can use, just use the simplest solution, and the databases that impose most restrictions are usually simpler to use. Okay, so another thing about Elixir that is sometimes not widely recognized is what is actually the let it crash philosophy. So Erlang and Elixir share this let it crash philosophy. And what does it mean is that when we write our programs, we almost always use the equal sign, which is the pattern matching operator, and it checks if whatever is on the left side whatever is on the right side has the shape of the thing that is on the left side. So if we want to write something to a file, it may either fail and return tuple of error and reason, or it can succeed and return OK. So what we do here is we don't try catch every possible error, because as we've seen on the keynote, complex system fails in complex ways. So we, instead of trying to check all the possible error cases, we ignore that. And in case something went wrong, the error handling is somewhere else. It's in the supervision tree, and we usually try to restart the process from the beginning. And it doesn't mean that we always ignore error cases. It's like file write can return error reason, for example, ino entry, and in case it's part of our business logic, we of course use it. So in case the file is there, we print success message. In case of error, we display dialog like, would you like to create that file? And that's totally okay, but it's still your business logic. So you're concerned with what you want to do, with your happy path. And you almost ignore all the other cases. And in case something is wrong, you try to restart it a couple of times. And if that doesn't work, then we go higher in the hierarchy, up to maybe actually crashing the application, but it happens very rarely. It's surprising how often just restarting something with fresh state just clears all the problems. For example, we use Heroku for deployment, and if you check their documentation, they say that dynos are restarted at least once per day to help maintain the health of applications running on Heroku. And the health of application, it basically means that there were some applications that had memory leaks. And in many cases, instead of letting them grow, they just restart them once in a while, and it just works. What's more, they also delete all the changes to local file system. So if the problem was introduced by writing to some file, it will also be deleted. And as I said, that solves surprisingly many problems, and it just makes your system more reliable, because in case of errors that, for example, database errors because of lost connectivity, you just retry, and you probably succeed if this is not a permanent error. And in case of permanent error, you're still screwed. Okay, but the problem with let it crash philosophy is, would you like to fly a plane that is programmed with let it crash philosophy in mind? Because I would, because the only programming language that I know has this philosophy is Erlang and Elixir by transition. And I know that it actually helps preventing problems and crashes, because what we usually associate crash with is this, like our application stops working and there's a blue screen of death, and it's terrible. However, if you look at the history of programming, like for example the Apollo 11 primary guidance, navigation and control system, they had this case where landing on the moon took 85% of CPU power. And the 15% was reserved for example, inputting commands by the crew. And checking the altitude, for example, was a command that needed to be run by the computer. However, there was a hardware bug in the radar system. So it used 13% additional CPU power. So basically, when they started the descent, there were almost no CPU power. It worked correctly, and when they tried to input a command to check what's the current altitude, the command crashed. And that was totally fine, because the scheduler was built around the notion of priorities, and landing and radar, which was necessary for this landing, had higher priority than commands that will be input by the crew. And this is the same case with let it crash philosophy in Erlang and Elixir. It contains the error in one place. It doesn't let it spread through your application and corrupt the data. So I like more, for example, when people say it's a happy case programming, or let it fail fast philosophy, because it just works better. And even Loic, who created Erlang web server, recently wrote a blog post about why let it crash is just the wrong choice of words from the marketing point of view. And I was like, dude, couldn't you publish this 2 weeks later? Now everyone will think I stole it. Okay, so how our system in Club Collect works. So the part that I'm currently working on will process transactions that will be sent by some other subsystems. It will be the server on this picture. So when we try to send a transaction to this server, it's not enough to just send it asynchronously, because the client really wants to know if it worked. So the server does some processing, accesses the DB, then again does some processing, and each of these steps can fail independently. So in case the first processing step fails, nothing is saved to the DB. In case last step of processing fails, we don't get the response. So what we usually do in such a case is that the client, when creating a transaction, first saves it locally on his disk, then performs the send operation, and then waits for a response and saves that response. And is it enough so that those two systems know that actually everything is processed and everyone knows about this transaction? And do you know the two generals problem? The problem is that if you have two armies and they need to attack the city that is in between them at the same point in time, and they need to send messengers to communicate that hour, it is extremely hard. Because let's say that the first general sends a messenger like, let's attack tomorrow at noon. Can they attack if the messenger got to the second general? No, they can't, because the first general doesn't know if the second one got the message. So the second one sends a confirmation. Yes, let's attack tomorrow at noon. Can they attack now? No, they still can't attack, because the second general knew that the first general will be hesitating until he gets the confirmation, and he doesn't know if the confirmation came in. So let's send the third messenger. Even if this third messenger goes through, now the second general doesn't know if the first general knows, and so on and so forth. Basically, even the infinite amount of messengers doesn't solve the problem. I mean, it increases confidence. At some point, they will be like, okay, there's 99% chance that we're attacking at the same time, but it's never 100%. And there are really complicated protocols to achieve synchronicity between two systems. However, we simply don't need them, because in client-server architecture, only one of the sides is really interested in the information being sent to the other. So the client wants to know that the server got the transaction. So in case something went wrong and the response wasn't saved, we should retry. And it's the client's responsibility. And server, it sends the response. However, it doesn't care if client got it. It's the client's responsibility to retry. And speaking of retrying, how can we make retrying with transactions? If we have something like create transaction endpoint, and we only specify the amount and from who to who the transaction should go, it's not enough, because in case of retry, we wouldn't know if this is like the same transaction or it is a new transaction just with the same values. So one way to solve that problem is to always generate IDs on the client side. So it's very common that REST APIs use post method and then return the ID of something that was created. And this is a problematic design because if we don't allow duplicates, it might be harmful if we don't get the response. So it's usually better to create the ID on the client side and then use it to send a message to the server. And this can be achieved using put method of HTTP requests. So we first created the UUID, then send the message, and we're pretty sure that even if we retry, we will get the same response because put guarantees that it will be idempotent. And we don't have to worry about IDs because unique identifiers, when they are created, the search space is so big that it's more probable that your old development team will be eaten by wolves in their respective flats than the keys will clash. Okay, so to sum up our development, how people see Elixir. It's great for distributed systems, it's great for complex stateful communication, and it's perfect for base databases. And how do we use Elixir at Club Collect? We have a single node service, we have a client server without state, and we use ACDB. So why the heck do we actually use Elixir? And it is because it has many other nice properties that are probably less marketed. So for example, one of them is that it keeps side effects in check because it's immutable. So testing in imperative programming usually includes setting up some state, running the tested code, and checking out the new state. In functional programming with immutability, it's always setting up a data structure, then running tested code, and then checking new data structure. So from the programmer's perspective, it's almost the same. It involves the same amount of work. However, if you want to run those tests, if you have a state that is shared at some point, you can't run those tests in parallel. And in functional programming, if you have just data structures, you can parallelize your tests, and that's pretty nice. Also, Elixir encourages programmer to write your programs in a certain way. So basically, there will be a set of transformations on data. So we start our pipe chain. This operator is called pipe operator, and it basically takes whatever is returned by the previous expression and puts it as the first argument of a function. So there will be a series of transformations where the first one will gather some data, for example, call external services, read something from database. Then there will be your logic that may be arbitrarily complicated, but it's good if it doesn't have any side effects because you can test it more easily. And then there's a point in your code where you return all your data at once. Again, calling external services or saving stuff to DB. And that is, for example, how plug works in Elixir. Plug is a library that is a base of Phoenix framework, and it abstracts away all the impure parts of handling HTTP. So you don't have to receive stuff from the socket. This is impure. You don't have to send it back. This is done by plug. What developer does, he only receives already parsed data structure called con for connection. And this con has everything that you need to know about this particular request. You set some other fields in this request, for example, status and response field, and then pass it back to plug. So at the end, testing something like plug is really straightforward. You set up the data structure, and there's usually helper for that. You then call getRequest, which tests almost entire stack because it goes through your router, through your controller, through the index action, and it returns the con, where you can check if it has proper HTTP status, proper HTTP response. So it's really nice for testing. There are, however, cases where you would like to do something impure inside these transformations. So let's say that in the middle, you really want to save something to database given some condition. So instead of directly saving stuff to database, you can defer sending this to this last point in your program. So basically what we want to do is to, apart from the data that we already need, pass one more data structure that will hold all operations to the database that we want to perform at the end. And in Elixir, there's an Ecto library that is database wrapper, and it has the concept of multi. Multi is a data structure that just keeps all the transactions that we want to do on the database in one place, and then we can run it in a context of transaction. So we pass this additional value, the multi, and the same as before, if the condition is true, we add to the multi the insert operation. However, if the condition is not true, we return the multi as it was. So if there were any operations there before, they will still be there. If it was empty, it will still be empty. And now we can test this without touching the database. We also set up the data structure as before. We run a given piece of code, and it returns both data and the multi. And at the end, we can assert that the data didn't change. This is the expected behavior, and then that the multi is there. And if you think about it, it's a really cool concept because it makes testing much faster. You can test for both positive and negative case, and you don't touch the database. And then you have like one integration test that really checks if this fits, if this connects. But those other cases and corner cases don't have to really touch the database during testing. There's also a situation that is the opposite, which is if you want to read something from database, and this is a little bit simpler. So instead of reading something just in this place, we can pass the module name that is our repository as a function argument. So what I did there is I made the repo lowercase, and I'm saying that the default value, this // will be the module repo. So in case of your application code, if you want to call it, nothing changed. You still call it with one argument, and then the default argument will be capital R repo, and it will do the thing you want to do. However, when you're testing it, you can pass the repo module explicitly. So you quickly create this repo module that will behave as Ecto repo, and then pass it as a second argument to this function. And then you can check your logic independently from the database. There are other benefits of Elixir for writing business logic, and this is firstly no callbacks. So Elixir tries to be very explicit, and at some point in time, people ask, for example, if they will be able to run some code when update operation on database is performed. And the answer was resounding no, because if you really want to do something like that, just make a function that firstly updates the database and then does your stuff and call it in your code. It will be very explicit. And also, if at some point in time there will be a place where you want to just perform the update, you won't be surprised that there is some side effects happening outside of your code. It also has great performance, and this is probably the reason why we are running it on just one node. So for example, there was a case of Bleacher Report who said that they had 50 servers running Ruby on Rails application, and they rewrote it to Elixir, and now they're running it on 5, and it's probably over-provisioned. That is quote from what they said. So this looks like a really great performance improvement, and this is what allows us to simply run it on one Heroku instance. The other thing is umbrella applications. So Elixir and Phoenix are trying to solve the problems that were before in Ruby community. And in Ruby community, it was very often the case that applications grew into these big monoliths. And in Phoenix now, it's very common to split your application into smaller sub-applications. And even though it is in one repository and can be started at one, it gives you some benefits of microservices. Because if you have application A that depends on B, application A can call stuff from the B application, but not the other way around. So it's a good way to isolate your code. And you have to think a little bit upfront about your design, and at the end it gives you many improvements of microservices without the hassle of actually deploying them and creating communication over HTTP. Of course, there are also some drawbacks. And for example, rapid evolution of language can be a disadvantage. So just recently, I needed to update Ecto to 2.3, and it required changing the arity of functions in all of our models, which was around 50 or 60 places. So even though it was almost easy to automate, I still did it by hand because I really wanted to check if I'm not missing something, and I needed to test it. Fortunately, we have a good test coverage, so I was pretty confident that it was okay. But you have to keep that in mind. The language evolves. So for example, the trick I showed with multi, we couldn't use it because when we started, the multi wasn't even a thing yet. So it's not in every place we would like it to be. Second thing is compilation time. So usually when you're developing, the iteration time is really quick because in Phoenix there is hot code reload, and this is very nice. But there are some problems with compiling. For example, if one module calls the other module, if the other changes, both need to be recompiled. So in extreme cases, for example, when you change configuration file that is also compiled, all your application is being recompiled. And that might be annoying, and it is also partially solved by the umbrella applications that you can simply test and run in isolation. But still, at some point, you need to run this build that checks everything and has integration test, and it just will be slower. Type system in Elixir is optional, and what I mean by that is that there is a tool called Dialyzer, which allows you to add type specs to your functions. And this is a pretty nice thing. However, it works best when all the dependencies are also statically checked by Dialyzer, and it's rarely the case. So Phoenix isn't, because it has so many libraries that aren't, and they won't be probably for a long time. However, I think that I'm more than happy to trade type safety for the performance and ease of development that Elixir gives us. Another thing is libraries, and I put a question mark there because actually there wasn't a library that wasn't available that I needed to, I don't know, write myself or search too long. There was only one case when I wanted to use Graphite where the library wasn't in the hex repository, and that meant that I had to manually resolve the dependencies. And at the end, I didn't use Graphite at all, so that didn't really matter. So to summary, what I want to tell you today is that Elixir needs success stories for companies that are smaller than Bleacher Report, that don't operate at scale, because Elixir is also a great language for just writing your normal crude applications. And it solves all the problems that Ruby can solve, and sometimes it even does it better. And in case of concurrency, there are things that Ruby just can't do because of global interpreter lock. And the second thing is that don't assume anything, not only about financial systems, but about any systems, if you're not 100% sure what the properties are, because we often assume too much, and at the end, we can shoot ourselves in the foot. So I think that's all I wanted to say. If you like this talk, you can follow me on Twitter. And if you want to know more about Club Collect or even work with us, now's the time for questions. Thank you.
Sorry for asking question before lunch. You have told us that it's a good language for available, highly available applications, and based on Erlang, and it's easily distributed. But do you know if there is a support in the language or in the libraries for vector clocks for communication for a casual consistency already done in this ecosystem?
If you really need this functionality, it's more than sure that you will find it, because it was built for that, and there are many libraries like that. I think that if you want to search for a particular one, I would recommend checking out React Core.
So I have one more question for you. You were talking about Elixir performance. So I have some problem with Erlang performance, and I think it's connected with Elixir performance. So maybe you know the answer. It's really true that when you are creating something in Erlang, you need usually less cores, and it works much better. But when we are running our system in very big scale, when we need a virtual machine that works on hardware with multiple cores, Erlang virtual machine have a lot of problem with mapping its schedulers to cores when there are multi-processor environment. If there are many cores of single processor, it works great. And where we have the same number of cores, but with more processors, for example, 2 processors with 6 cores instead 1 with 12 cores, the performance drops very much. So do you notice similar problems in your career?
So personally, I haven't, so I'm not sure I will be able to answer your questions. I believe that there are some flags to the virtual machine that should be used to allow it, and in worst case scenario, it might be beneficial to simply run 2 instances of Erlang virtual machine, both running on the single processor using its all cores, and just interconnect between them. But as I said, that is an extreme solution, I think, and I think there are people on the audience that are more qualified to answer that question, so I will put you in contact with them.
So, and what was the largest environment you were using? How many cores, processors?
So I remember that I was testing Disco MapReduce framework, and it was on the AGH, University of Science and Technology. And even though I don't remember the details, I think that it wasn't run on the supercomputer, it was run on the cluster of smaller computers. So the one machine with there wasn't the case that I was running it on one machine with many processors. It was rather clustering it on small commodity hardware, because that's usually cheaper. That's what Google also does for their environments.